there's a lot going on in this example. We're given a function f of t equals 18t minus 3t squared. And we want to deeply analyze this thing. So let's read through this. Position, velocity, and acceleration. Suppose the position of an object moving horizontally along a line after t seconds is given by the following functions. S equals f of t, where s is measured in feet, with s greater than 0 corresponding to positions to the right of the origin. Okay, so what that tells us is this f of t, right, is the same thing as s of t, which is position. So s of t, and we're going to call this position. Okay, and then the example is going to ask us to do a whole bunch of things, analyzing the position, velocity, and acceleration of this particle that's moving left and right. So just to visualize it a little bit, right? You just think of it as, right, you have some particle on a string or on a rod essentially, and it's moving left and right here. Okay, and we'll dig a little deeper into that. The important thing to note here is that you have the position, s of t. Well, the derivative of the position is velocity. We'll call v of t velocity, aka speed, essentially. And then you can take the derivative of velocity, so d by dt of v of t, and you get a of t, acceleration. So that's what we are, acceleration. Okay, so that's the essence of what we need to know to move forward with this example. Position, velocity, and acceleration are all found. Well, you start with position, take the derivative, that's velocity, take the derivative of that, you have acceleration. That realization alone opens up a ton of physics. It paves the way for Newton's laws and allows us to predict where a particle will be as a function of time, or an object will be, for instance, a rocket or a satellite. So, you know, it's really profound, this realization of how position, velocity, and acceleration are linked. So let's step through this example one piece at a time, starting with part A. Part A says graph the position function, and this f of t is the position function, and it's actually a parabola. Believe it or not, it might not look like it, but let's rewrite it. F of t equals negative 3t squared plus 18t. And now you can see that perhaps this is a parabola because of the t squared, and this negative 3 in front tells us that it opens down. Okay, so it opens down, and let's graph this parabola. So we're going to have to reach back to some of our algebra skills and remember how to graph these parabolas. Remember that we need the vertex, right? The vertex is one way to do this. That's certainly the most direct way. And the x-coordinate of the vertex, or in our case, the t-coordinate of the vertex, is given by negative b over 2a. So in our example, negative 3 is our a, 18 is our b. So then we can solve for t. That gives us negative 18 over 2 times negative 3, which comes to 3. So there's the t-coordinate. To get our position at t equals 3, we plug that in. So then we say f of 3. Okay, so we're plugging that into this function, and it turns out that gives us 27. So we combine these two things for our vertex, 3, 27. All right, that's a good start. Next, we need our x-intercepts, or I guess we'll call these our t-intercepts. T-ints. Okay, so to do that, we set the whole thing equal to 0. 0 equals negative 3t squared plus 18t. Remember, you always set the opposite variable equal to 0. So when we want the t-intercepts, we're going to set, I guess, f of t equal to 0 and then solve for t. We can factor out a negative 3t here. That leaves us with t minus 6. And then we can see that our intercepts are t equals 0 and 6. So that's good. So we have a parabola opening down. We now have our t-intercepts and our vertex. We actually also have our f of t, or our position intercept as well, or you could think of that as our y-intercept. But that could be found by computing f of 0. So I'm just going to say the y-intercept, even though there's not really a y here, but just to keep it distinct from our t-intercepts, let's do f of 0, which is 0, which we already knew because we have our 0 up here. So let's put all this together on a graph. Okay, we have 1, 2, 3, 4, 5, 6. All right, so we have our intercepts here at 0 and 6, and then way up here at 27. That's our vertex at 327. So how about right about here, 327. And then we're going to keep going until this is 6, until x equals 8. Okay, so our parabola, you can kind of see it forming here. It comes up like so, and then comes down, and it looks kind of funny. I'm actually going to replace this. It's really hard to draw parabolas on this writing tablet, so at this point I'm just going to replace it with the Desmos graph rather than try to keep drawing this parabola. There we go. There's the nice version of this function. Our so-called x-axis here is our t, and then the y will be f of t, position. So we have time and position. And with these kinds of examples, it's nice to kind of picture what happens as your object moves in this left-right plane. So it looks like we start at 0, 0, and the object comes to the right and then turns around and goes back to the left in time. So it turns around here at t equals 3 seconds, and it goes out to how far out does it go to the right? To 27, and we're working in feet in this case. And then at 8 seconds it stops, so we'll say here t equals 8, and it goes all the way down here to negative 48 in the left. So the object starts moving out in the right direction and then gets pulled back into the left direction. Just to get an idea mentally of what's happening with this. You can think of it as like a bead on a string or something. You know, I kind of added an extra dimension here just so we can see how it's folding back on itself. But really, you would just be moving out and then coming right back on top of itself. Let's move on to part B. In part B, we're asked to find and graph the velocity function, and then we want to answer when the object is stationary and moving to the right and moving to the left. And as a reminder, we're given the original function f of t equals 18t minus 3t squared, and we're interested in the time interval between 0 and 8 seconds. Well, velocity is the derivative of position, so we can essentially just say velocity as a function of time will be let's just say df dt. Okay, and f of t, of course, is given here, so that's a pretty quick derivative, 18 minus 6t. And that's a line, which is a little more obvious if we write it as v of t equals negative 6t plus 18. Okay, so there's the velocity function. Let's analyze this a little bit. It first asks us to graph it. Well, that's a line. Let's do it. So we have our function here. I'm going to graph it using intercepts. Clearly the y-intercept is 18, so that's going to be somewhere up here. To get the x-intercept, we set the whole thing equal to 0, so 0 equals negative 6t plus 18. Solving that for t gives us t equals 3. So 3, something like that. We need one other point, and that's to figure out where this line stops, because we're only examining the time between 0 and 8. We already know at 0 we're at 18 feet per second are the units in this particular example. But what happens at 8? So we need to compute v of 8, which turns out to be negative 30. Negative 30 there. So we have another point way out here at 8 seconds and negative 30. So these will make a line. I'm going to let Desmos do the work for us because it'll make a much nicer line. So we can see from the graph here that up here where the velocity is positive, we're going to call that the right direction, moving right. And down here where it's negative, all this stuff, we'll say moving left. Okay, left. And it's stationary at this one point here. Right, at t equals 3 seconds, is changing directions. So at that instant when it changes directions, it needs to be stationary. So we'll call that stationary. So let's write our answer slightly more mathematically here. We'll say from 0 to 3, we're moving to the right. I'm including 0 because even at 0, we're still up in the positive direction here. Then at t equals 3, we're stationary. And finally at, let's see, between 3 and 8, and again I'm going to include 8 but not 3, we're moving to the left because then we're down in that negative direction. Let's move on to part C. Determine the velocity and acceleration of the object at t equals 1. We'll recall that the velocity as a function of time from part B was negative 6t plus 18. So we can very quickly determine v of 1 to be, well, that's negative 6 plus 18, so 12, and we're in feet per second here. It says that at the very beginning, at the very original statement of the problem. So there's velocity at 1 second. Now acceleration is a different story here. To get the acceleration as a function of time, we're going to take dv dt. Okay, well, the velocity is negative 6t plus 18, so the derivative of that is simply negative 6. So this tells us that the acceleration is a constant pole of negative 6. Well, so then a of 1 is still negative 6. And we should add some units here. Units of acceleration are always distance per time squared. So this will be feet per second squared. So there's our acceleration at 1 second. That would be our acceleration at 5 seconds. Acceleration at 3 seconds is all going to be negative 6. That may seem a little strange, but actually it's not. Just imagine gravity. Right? Gravity is a constant acceleration down. So we're actually used to seeing a constant acceleration. It would be more strange to us if acceleration were changing. That would be less intuitive. Part D immediately follows from this realization about acceleration. Part D asks us to determine the acceleration of the object when its velocity is 0. Well, we know from part B that velocity was 0 when t equals 3. That's when it's turning around. But acceleration at 3 seconds is still negative 6 feet per second squared, because that's what it always is. So again, constant acceleration regardless of time. Part E asks, on what intervals is the speed increasing? The key to figure out where speed is increasing is to note where velocity and acceleration have the same sign. The same sign. That's what makes it all come together. Let's try and intuit what's happening here physically. Right, so let's see, we need something more like this. So we have some kind of force back here, like maybe a magnet or something, right? And it's pulling to the left, but the particle shoots off to the right here. Right, it goes off like this, and then at 3 seconds, this is just kind of a visual representation of what happens. It turns around and gets pulled back, and then goes faster and faster and faster off to the left. So the acceleration is always in the left direction physically. It's pulling us to the left. It's a negative 6 acceleration, but the velocity initially starts out in the right direction, but the acceleration is pulling it back. So it's going to slow down, slow down, slow down, and then at t equals 3, it turns around and then it starts going off to the left. So it's slowing down when it's moving in the positive direction. So right here initially, v is positive, a is negative. So it's getting slowed down. And then it turns around, and then for this whole time here, velocity is negative and acceleration is negative, because acceleration is always negative. So once it makes that turnaround, then this particle is just going faster and faster and faster and faster as it kind of gets shot off to the left here. So physically, that's what's happening. Now recall that acceleration in this example was -6 feet per second squared, and velocity, we'll call that velocity as a function of t, was -6t plus 18, which recall that the graph of this thing was a line that is given here. And remember that velocity was negative, so again we're interested in the negative direction because we want it to match acceleration. So velocity was negative on this interval down here, where it's below the x-axis. So we're talking about from 3 up to 8. So speed is increasing when the sign of acceleration and velocity match. In this case, that is from 3 to 8 seconds. The speed is increasing. Notice that I didn't include t equals 3 because if you recall from, I believe it was part B, that's when the object is actually stationary, which makes sense from our little diagram here because we can see that's where it turns around. So for that brief second at t equals 3, the object is actually stopped. Even though the acceleration is still pulling it to the left, it stops just for a brief instant at 3 seconds.